Okay, so we are looking at Majorana fermions in the previous lecture. So we introduced Majorana fermions because we thought that we want to find the motivation for Majorana, whatever way you want to call him, because J is pronounced as Y in some parts of the world. Essentially, J is pronounced as Y. So what Majorana wanted to look for a solution to the Dirac equation in which the wave functions are real, just like in Klein-Gordon equation. The Klein-Gordon equation, which we have seen, has a real scalar particle as a solution. You can make complex scalar fields, but the complex scalar fields can be decoupled in the absence of interactions, can be decoupled even in the presence of interactions, also can be decoupled into two real wave functions, but in strictest sense in the absence of interactions, because in the presence of interactions they are like particle and antiparticle pair essentially. So the complex scalar field also can be decoupled into real and imaginary parts, which can be thought of as two independent scalar fields, and you can work on it. So for Majorana it was very crucial to find real solutions of the Dirac equation. So what he realized was, because there is an I in front of the del slash, okay, here essentially, which is I gamma mu del mu. So if somehow the gamma matrices are made completely imaginary, so if the gamma matrices are completely imaginary, then psi and psi star would also become real solutions essentially. Now he went ahead and found a class of solutions. Actually so he found as a representation which is called the Majorana representation, which is given as follows. So I want to distinguish within the Dirac representation, which we saw it earlier, and so that is the reason why I put a tilde on the top and I calling it as Majorana representation. So the Majorana representation has gamma 0 given by sigma 2 in the off diagonal, and gamma 1 given by I sigma 1 in the diagonal, and gamma 2 given by sigma 2 in the off diagonal with the minus sign for the second part, essentially second time the sigma 2 appears, and gamma 3 is equal to I sigma 3. So this representation is called Majorana representation, which has all the gamma matrices completely imaginary. Now you put it back into the Dirac equation and you see that representations as wherever there psi is a solution, psi star is also a solution. That not only that, the solutions are equal, the wave functions which are equation solutions of psi and psi star are equal essentially. So then of course good, we found the real solutions of the Dirac equation. Now the next question is the representation unique? What are the implications? And of course you can also ask, where are the applications essentially. Okay. Now let us look at the first question first. Essentially, is this representation unique? The answer is no, because you have different representations of gamma. This is not the only unique way of writing gamma matrices which are completely imaginary. This is not the only way, okay. You can always find several solutions in which say for example you can okay, so you can interchange sigma 2 by sigma 1, sigma 3 by sigma 1 by sigma 3, sigma 3 by sigma 1, and so this is possible. So that essentially sigma 1 and sigma 3, if you interchange, that gives you one representation. or if you interchange sigma 2 and sigma 3, that gives you with I sigma, that gives you another representation. So, interchange of sigma matrices in this form of this thing, okay, itself gives you another representation. So, the answer is this representation is not unique. So, whenever we interchange, so gamma matrices, this is in general true for any gamma matrix, any representation of gamma matrices, they are not unique, and this is not special for only for Majorana representation. It is true for Dirac representation, it is true for Weil representation, it is true for chiral representation, it is true for all representations of uh, of uh, of, uh, of gamma matrices, that they are not unique. You can always go from one representation to another another form of, say, the same within the Majorana representation itself. You can keep moving from one representation to another by the simple exchange of sigma matrices or gamma matrices, such that your commutation relations are still valid. Essentially your commutation relations are still valid, and that freedom exists between sigma 1, sigma 2 and sigma 3, or gamma 1, gamma 2 and gamma 3. So, within the Majorana representation, even this is not unique essentially, and all the gamma matrices are related to each other, all the representation are related to the representations of the Majorana representation. Now, this is too much use of word representation by a similarity transformation So, in other words, you can always think gamma mu is equal to u gamma u tilde, so u dagger, where u is a unitary matrix. So, you can always change one representation to another, okay, by choosing a particular unitary matrix essentially. So, yeah, so in general, so this is the most general form of the Majorana representation, most So, what does it mean? If I write something like this, that means which is an undefined unitary matrix. So, I did not define what is this u. So, what I said is that you can always define the Majorana matrix or all imaginary representation of gamma matrices or up to a undefined unitary matrix. So, all gamma matrices, here there are 4 of them, are defined up to a unitary transformation. So, that means if the gamma mu, if I use now this gamma mu instead of gamma tilde, if I use this gamma mu, my psi would be u psi tilde. So, the my wave function is also well defined as a Majorana representation up to a unitary transformation. So, up to a unitary transformation. If that is the case, how will how will how will the real condition of the wave function appears? How will the real condition of the wave functions appear? Then you can see that you have, so you have psi tilde is equal to psi tilde star. So, instead of that you have u psi is equal to u psi star, or psi is equal to u psi, right, essentially. So, we used psi is equal to u psi tilde, or psi tilde would be u dagger psi, psi tilde will be u dagger psi. So, u dagger psi would be u dagger psi star, that means psi is equal to u dagger psi star. So, the real condition is the original condition, this is psi tilde is equal to psi star tilde, but now taking into the consideration the unitarity picture, essentially the unitarity rotation. So, this gives me psi is equal to u dagger psi star. Now, what I do, I will introduce something called u dagger is equal to gamma 0 c, where c is another unitary operator which is called charged conjugation operator, and this gives me the condition psi is equal to gamma 0 psi c psi star. So, this is the Majorana condition or the Majorana condition, okay, and this is the condition. What we want to say essentially is that the right combination, right hand side should become something called gamma 0 psi, and left hand side we can call it as psi cap, essentially just to make it as something else. So, instead of psi we call it as psi c, is equal to psi c, we will call it as psi c, and this is the introduction of the charge conjugation operator. And this, what does the charge conjugation do? Charge conjugation operator tells you that psi is, and this the original condition, okay. So, the original condition, if we call this psi, so this is the, okay, let me go back to this thing. So, psi is equal to u dagger u psi star. Now, u dagger u is equal to gamma 0 psi c, gamma 0 is psi c, and I call the left hand side, right hand side, the RHS is called as psi c is equal to gamma 0 c psi star, psi c is equal to gamma 0 c psi star. So, equation 1 becomes So, the Marrone condition becomes psi is equal to psi c. So, this is the most important condition. Okay. So, what we saw, the reality condition gets modified into a condition on the in terms of the charge conjugation operator. The reality condition gets modified in terms of a charge conjugation operator. Okay. So, again let me trace back this thing, this is important to know, understand that. So, what I said was that a gamma matrix representation is not unique, because all the representations of all Marrone representations, if you want to, are related by a similarity transformation. So, you can always have exchange of you can think of some unitary rotation of this sigma 1, sigma 2, sigma 3 and everything. So, they keep changing themselves. So, sigma gamma 0 gamma mu becomes so gamma mu can be transformed into something as some u gamma tilde mu u dagger, and it will have the same solutions. So, U will be a unitary matrix. So, it will have some unitary matrix which rotation which gives you some the same condition essentially. So, this means that all the gamma matrices are defined up to a unitary transformation. If that is the case, the wave functions are also defined up to unitary transformation, up to a unitary transformation psi is equal to u tilde u times psi tilde. Now, if that is the case, the condition of psi tilde is equal to psi tilde is equal to psi tilde star. How does this appear? So, psi tilde star is equal to, this is the condition we started with, psi tilde is equal to psi tilde star, this is the condition we started with. So, let me call this as original equation 1. This is 2 say for example. So, this substituting what is the definition of u psi is equal to u psi tilde into this equation, we ended up having this relation, and this gives me psi is equal to u dagger psi tilde psi star. Now, this is not u dagger, this is u transpose. There is a difference, u dagger is equal to 1 and u transpose is not equal to 1. That is the crucial point I wanted to make, because there is a star sitting here. So, on the top of the dagger, so this just becomes u transpose. Now, defining u transpose, okay, I think this should be made clear, this should be u transpose. I think my writing was not so clear. So, u dagger is equal to 1, and because it is a unitary matrix, but u transpose is not equal to 1, this is the crucial point. Okay. So, that means this matrix is complex symmetric, essentially it is complex symmetric, it is not unitary essentially. Okay, u transpose is equal to gamma 0, again you write it as gamma 0 times c. C is another unitary operator or a matrix I am defining, I am not defining what it is, it depends. Okay. You will see that there are C is also a matrix made up of gamma matrices, as you will see. C is also some matrix made up of, you can have representation made up of in terms of gamma matrices. So, the common one would be I sigma gamma 0 gamma 2. Okay. So, I define the right hand side is as gamma 0 C psi star is equal to psi c is called as, is defined as essentially. So, this is the definition. So, what does this do? This is called a charge conjugation operator. The charge conjugation operator transforms all the particles, all the wave functions, the wave u wave functions to v wave function, antiparticle wave functions. Okay. The charge conjugation operator actually changes all the all the quantum numbers of the particle into those of the antiparticle. Okay. Now, okay. So, this is the reason why I want to call it as a special operator. It comes out as some sort of a, in fact the way I introduced, I did not introduce it as an special operator like P. It turns out that under the Lorentz transformation, P, C and T are discrete symmetries of the Dirac equation. Okay. The charge conjugation is one of the few important discrete symmetries which the Dirac equation or the Dirac Lagrangian possesses. But the way we introduced it is in terms of simple unitary complex unitary matrix, essentially complex unitary matrix, complex symmetry matrix, and so this is UU transpose gamma 0 C. This we call it as the modified wave function, and the operated wave function is given in terms of psi c. So, the Majorana condition, psi is equal to psi star. So, that becomes psi is equal to psi c. So, that becomes psi is equal to psi c. Now, given the information I have just given you, the operator C is a charge conjugation operator. It transforms particles wave functions to antiparticle wave functions and subsequently as a consequence particle quantum numbers are modified into antiparticle quantum numbers so are transformed or modified or moved. Okay. So, they become antiparticle quantum transfer number. Now, given this information, what does this tells you? That this condition, the Majorana condition, tells you that the particle wave function should be equivalent to the antiparticle wave function, and the particle quantum numbers should be equivalent to the antiparticle quantum numbers. So, we are now ready to understand the implications. The second part question we asked, the C operator so the implications are, okay, this we have already seen. Essentially the implications are psi is equal to psi c implies 1, the particle wave functions should become antiparticle wave functions. 2, we will see this in more greater detail. Essentially the particle quantum numbers and should be equivalent to antiparticle quantum numbers. So the first one is obvious that that means u and v wave functions should be equivalent. Now we will see the notation what it means that for Marana fermions, because u would become u v star essentially and so on so essentially, and the particle quantum numbers should become antiparticle quantum. When is this possible? So if a negative energy, suppose imagine that electron has a negative energy essentially. So when is this possible? Okay, this is only possible when the second part is only possible when electric charge of the particle is 0. So when the electric charge of the particle is 0, then the particle wave function can become antiparticle wave function and its quantum numbers can be equivalent to that of the antiparticle wave functions essentially. Okay. So this is only possible when particle wave functions and antiparticle when for neutral particles. So what we have learned today is that neutral particles can be Marana fermions essentially. So neutral particles can be Marana fermions, okay, and so what it means is that their particle wave functions can be the same as the antiparticle wave functions, and if they are neutral because their electric charges should be also be the same. So this is only possible if they do not have any electrical charges possible. So that is exactly what happens for neutral particles, they do not have any electrical charges. So such kind of particle examples are neutrino, the example which we have seen just now, then neutron, etc. So these are the examples of neutral particles, okay, which can be their own antiparticles essentially, their own Now in physics we already have seen an example of a particle being its own antiparticle, but it is not a Marana particle because Marana particle is only for a spin half particle. For example, gauge boson, which is the gauge boson which is a photon essentially, the photon is its own antiparticle. Photon is a chargeless neutral particle, but it is not a Marana fermion because Marana fermions are spin half particles. So neutral spin half particles which are their own antiparticles form Marana fermions. Neutral spin half particles which are their own antiparticles, okay, form Marana fermions. So let me just make this statement and then we will continue with the discussion a little bit more. Good. Now still several questions appear. Where does, what has this to do with neutrinos? Essentially, why should neutrinos could be their own antiparticles? As we will see, the situation is a bit more complicated, because whether a particular particle is Majorana or not also depends. If it is massless, it is typically a Weyl fermion. Can a Weyl fermion be also a Majorana fermion? These are all issues which we will deal with. Essentially, we will discuss these questions in some of them will be given as homeworks and everything essentially. Okay. But the example of neutrinos, in the case of neutrinos in 4 dimensions essentially, and because we are dealing with 4 okay, whether neutrinos are Majorana fermions or Weyl fermions will depend upon whether they have a mass or not. If they have a mass, that means they could be Majorana fermions or Dirac fermions. If they do not have a mass, they are definitely Weyl fermions. Okay. In 4 dimensions, this is the definition. So, Majorana fermions or Dirac fermions depend upon how they attain their masses in 4 dimensions, and whether they are Weyl fermions, that means they are purely massless fermions essentially. Okay, good. So, we will talk about neutrinos a little bit more, and I will also talk about the charge conjugation matrix, and then we will continue the discussion about the Majorana fermions in the next lecture. Okay. Thank you.